Good afternoon. This is CIVE632, Computational Hydraulics and Hydrology. And today is November 22nd, 2021. And this is the beginning of the 14th week. We have this week, which is holiday. We don't have a class Wednesday because of the Thanksgiving holiday. And then we have another set of classes next week, and that's it. So I had briefly introduced this subject last Wednesday. So let me just reintroduce the subject. In 1993, let's see, there was an event in 1993 in Arizona, which we're going to talk about extensively today. And that called the people in charge of the hydrology in southern Arizona, that is Pima County. It's actually the Pima County Transportation and Flood Control District. They inquired about modeling, and we said we had just developed a model. And I happen to know some people out there, and so they basically gave me this contract to use the model for the first time. It was interesting. So that's the story that I'm going to tell you today, how we use that model for the first time in the Santa Cruz River Basin in Arizona to model, simulate, get an answer out of the hydrology out there so that they could design a couple of bridges that had been damaged by the flood. It was a very bad flood. Well, we have a lot of bad floods, but I mean, everywhere, not just here in the United States. We have not really solved the problem of floods. I don't think we can solve it. We're just trying to do the best we can. The reason should be obvious. The floodplain is usually big. Look at the Mississippi, it's a huge floodplain. And it's called floodplain because it was generated with floods. So the tendency is for it to be flooded every once in a while, every few years, 5 years, 10 years, 15 years. And it's within the realm of us experiencing it. I mean, we may be out there 25, 50 years and still we're gonna catch it at least once, or we're gonna experience it at least once. So that's what it is. So a lot of the stuff that we're doing here is to try to learn the hydrology, the hydraulics and the hydrology, and then to try to apply these concepts to determine values that we should design with. Because structures in engineering and civil engineering are designed with criteria. The flood control criteria, 100-year flood, PMP, etc. And engineers have to calculate these values. And that's what we're going to be doing today, calculated values for design purposes. So let's take a look at the abstract here. A case study of large basin hydrology. Large basin hydrology. Let's remind ourselves that Professor Ponce wrote this paper in 1985. So that is exactly 36 years ago. I was a very young person at the time. That's half of my life, almost exactly half. So there's a few things in there that are somewhat different than what I would say, the way I would say it today. However, we have, after 35 years of experience, however, we have remained or have not changed this paper. This paper in HTML is exactly the paper in the original version. If you want to see the original version, it's right there, right? The original version, black and white presentation. But we like the color and we like the capability to expand it and it's more flexible. I don't think I have to convince you that this tool that we're using with HTML is better than what we had before. So the basin of the Santa Cruz River, it drains 3,500 square miles. That's about as large as I have modeled. I've modeled quite a few basins, but 3,500 square miles is a lot. You have to multiply that by 2.58 to get the square kilometers. So that's about 9,000 square kilometers. Actually, I take that back. When we did the Paraguay, the the upper Paraguay, it was a lot bigger than that. It was a lot bigger than that. But we were not doing, I have to take that back. We did the entire Paraguay, not with a model that I had developed, but we ran a model. And the upper Paraguay is about 500,000 square kilometers. So 200,000 square miles. So this is a lot bigger than what we have in here. But so be it, or as the case may be, we can compare sizes of watersheds and basins. And that's exactly what I decided to do in my book in the year 1989, to classify all watersheds into small, medium, and large. And I'll have a chance to expand on this concept later on for those of you that have not had access to my hydrology book or had not taken a basic hydrology course from me. Okay, evaluation uses novel techniques of deterministic hydrologic modeling to calculate frequency-based flows that propose bridge improvement sites. Why deterministic? And by the way, I intend to use half of the time on this paper and half of the other one, so I'm going to watch the clock in here. Why deterministic? Because at the time, we realized that you could do frequency analysis, and there had been a few people that had done frequency analysis on the Santa Cruz Basin. Frequency analysis was very common at that time. Frequency analysis started with, I believe in the year 1910, 1915, where the first, Mr. Pearson was one of the first ones that really gave a lot of himself to study frequency analysis as early as 1910, 1915. So frequency analysis is a subject that is very well established. But it precedes the use of the computer. At that time, there were no computers. Now, when computers became available in the year 1960, 1970, and 1980s, particularly 1980s, at that time, there was a lot of software that was already available, and people started using the deterministic formulas, which is not frequency analysis, into the calculation. So more detail, a lot more detail, a lot more calculation. We had a computer, we had to use it. We wanted to use the computer. Let's not forget, for instance, that it was in 1968, only in 1968, that the Army Corps of Engineers created the Hydrologic Engineering Center, which devoted themselves, those gentlemen over there, ladies and gentlemen over there, devoted themselves to developing hydrologic software for their own use, but they didn't mind that the rest of the country and the rest of the world, as a matter of fact, was going to use it eventually, because they give it away basically for free. They allow you to download it. Sure enough, they don't give you any advice on the use, but they figure the users of these models should know hydrology. They should be technically oriented people, hydrologic engineers, hydraulic engineers, civil engineers. Of course, they can't stop anybody from using the model, but that's not their problem, right? Anybody can use the model. I've had solicitations by people in town that are not engineers, and they want us to help them because they cannot run it. It gets to the point where it becomes tricky to run any of these models, and if it starts failing, if you don't know what you're doing, then you can't do it, basically. That happens all the time. So let's go back. So deterministic is a new word that came about in the 60s with the advent of Wooding and Shackey and Woolheiser that allowed us to do these calculations. So we followed in 1985, and we call it deterministic, as opposed to stochastic, or as opposed to statistical, more statistical. Because I do not believe, I could be wrong on this because I'm not a stochastic man, but I do not believe there's not a whole lot of methods out there that are stochastic in nature that are used for floods. You know, hydrology is very broad. Floods is only one part of hydrology. You have daily flows, monthly flows, and all sorts of other stuff, right? So stochastic was out of the situation. So, well said, we call it deterministic. We also call it deterministic, but because we introduced for the first time, I believe, in practice, the use of the Muskingum conch. Let's not forget that I had basically helped develop the Muskingum conch and put it into practice. That was in the year 79. So this was 85. That was only 6 years later. So we used the Muskingum conch in here, which at the time, the Army Corps had not gotten into yet. And I'll tell the story later on. So computer model capable of simultaneously handling the complex topology of the basin. And we developed the concept of topology. I do not believe the Army Corps has what I call generalized topology. They have certain incipient development in the topologic area. What is topology? Topology is a system that allows you to determine the anatomy of the watershed, of the dendritic system, so that you can run the model without touching it, basically. You just give all the data for all the basins, sub-basins, et cetera, and then the model runs. As a matter of fact, this model that we have, since it's Fortran-based, it runs all this stuff in a few seconds, like a couple, 3 seconds. I don't think any run that I have done has taken more than 3 seconds. It is really amazing, the speed at which these calculations can be made, particularly nowadays. It used to be 30 years ago where the computers were, the servers were slow. I remember back in the year 1998, we had a server and it was slow. We had a server that had been given as a hand-me-down. I remember that. It had been given to me by somebody that wasn't using it, and I was using the server, and it was not very fast server. So that's when I developed the idea of actually creating the Visual Lab, because I asked for and got a fast server of the time. And we got it, and I decided that this was something, a server, you know. I do not believe that at the time that faculty were using servers. And nowadays, the issue of, I don't want to sidetrack the discussion, but the issue of a server is actually a situation that some people agree, some people disagree. I'm not going to get into that discussion. But the point is, we got a server, we installed the Visual Lab, and we were able to handle these things very effectively. But at the time, we were using just a computer of the time. You remember at the time, we had the fancy computers at the time were called digital equipment, DEC, Digital Equipment Corporation, which of course do not exist anymore. They went away in the early 1900s, 1990s, because of competition in the computer industry. Okay, so model complex topology. So we're going to talk about complex topology. 100-year frequency National Weather Service rainfall events, model calibrated using rainfall data for the flood of October 1983. We wanted to be able to simulate the flood of October so that we can progress and determine the floods for the next, the 100-year floods for the future. And you'll see why this was necessary. You'll see why they called me to do this thing. They wanted to do modeling. The people in charge out there wanted to do modeling. They did not want to do any more frequency analysis because they had 4 frequency analyses done over the years, and they were all different and sizably different, meaning they came out with different answers using these formulas were too, I guess you could say, too simple. That's the way they could be characterized. So, okay, so critical peak flows at bridge sites. There were 2 bridge sites that needed to be determined. And why determined? Because the bridges were destroyed by the flood. So they needed to be designed with a different discharge, probably much larger, certainly much larger. So that's why they hired us, or hired me, to do this work in the year 1980. I believe it was the year 1984, because this paper was published in 85. So the work had to be done in 84. Okay. So the use of deterministic, I'm going to head out here rather quick. Use of deterministic methods of recognized practice. Deterministic methods are not limited to the calculation of frequency-based floods. They also could be done, or could be performed to calculate PMF, which is related to the PMP, I'm sorry. PMF is probable maximum flood, which comes from the probable maximum precipitation. The problem of maximum precipitation is a concept that was developed in the early 1960s by the National Weather Service, NOAA, National Weather Service, because they felt at the time that they wanted to do hydrology for 1,000 years, 5,000 years, 10,000 years, and they didn't want to do it with 50 years of data or 100 years of data. When we collected the Santa Cruz River data back in the year 1985, we had 80 years of data. 80 years of data. So that means that in Arizona, they started measuring in 1905, which is understood because in the year 1900, Arizona practically did not exist as a state, let alone as institutions designed to do that. So there's not a whole lot of history in the United States, particularly in the Western United States, in terms of records. So you have 50 years of records, 80 years of records, perhaps since time has gone by, perhaps even 100 years of record. But that's not enough to extrapolate to 10,000, because everybody knows that the larger the extrapolation, the less accurate the answer is going to be. You have 100 years of sampling and you want to extrapolate with 10,000. So the National Weather Service decided to do an absolute value, not frequency-based. And they called in the meteorologists and they asked them the question, what is the worst possible, physically possible flood or rain storm that could happen? And they did all this calculation. They started with, I believe there was one state, I don't recall the name of the state, which had the first report, the early report in the early 1960s. This is all part of the record. And then followed with California, 1963. And then after that, they followed with all the others. And by now, by the 1980s, middle 1980s, they had just about every state of the union. They had developed PMP. And then they started changing it. And in 1998, they changed the California PMP because it was one of the early ones done, perhaps the earlier one. Well, one or number two, the California PMP. And then 35 years later, they decided that they had made a mistake or they had some omission, they had more data, and they changed the California PMP. And I happen to know because I wrote my book in the year 1989, and I put in there the old 1963 California PMP. And then in 1998, when I decided to do the second ed of my book, which by the way, is the one project, perhaps the only project that I never completed. I ran out of steam. Then I checked with the NWS, and sure enough, they had a completely different method for the California PMP, which I had to get into and study it and redo it. And I did redo it. I have a version. I'm going to say that I'm in the process of finishing up the book, and I probably will never finish it. It'll just stay incomplete work. But chapter 14, which has the California PMP, is out there. Besides, if you don't have to follow the book. You can go directly to the California PMP, which must be on the web. But all I did was just to spell it out in a more clear fashion, in a clearer fashion, which in the report, 1998 report on the new California PMP. By enough said about that. For basins exceeding 1,000 square miles, the task of simulating by the deterministic methods can be highly complex because we classify the approaches in hydrology, in flood hydrology, into small basins, mid-size, and large. Small was the one that, for the range or the realm of applicability of that rational method. The rational method had been developed in the year 1889, had been used for many years until the early 1930s, when Sherman decided that he was doing calculations of floods for mid-sized basins, or actually Sherman was using 2,000 square miles basins, which at the time were large. But at any rate, he decided that he could not count on the rational method because it was too simple. It was 3 values, CIA. What can you do with CIA, right? And therefore, he sat down and developed the concept of the unit hydrograph, which has implicit in it the concept of runoff diffusion, which I talk about in my book extensively. Basically, Sherman was out to calculate runoff diffusion. He didn't call it that way. He called it unit hydrograph. But the unit hydrograph, all it does is to calculate runoff diffusion. Okay, it's a diffusion of the runoff. Because Mr. Krieger, whom I may have already talked about in this class, or maybe in some other class, I believe in the hydrology class last year, had already told us in the year 1930-35 that the rational method was not accurate. And he developed a formula, which is called the Krieger formula, which is also very simple, which has nothing to do with theory, it's all practice. He plotted in one chart the flood discharge per unit of area over the size of the basin. And he ended up with a formula, which was called the Krieger formula, which some people like and some people don't like. Actually, most people don't like the Krieger formula. And the reason is because it is old. It's 1935, the Krieger formula. However, Professor Ponce likes it because the Krieger formula tells us in no uncertain terms that there is such a thing as runoff diffusion in the world. And I can talk about it extensively, but I'm not going to. We will sidetrack. Okay, so the Krieger formula is the EKG for runoff diffusion. Runoff diffusion is there because of the Krieger formula. Now, drop the Krieger formula, and now we're going to use for the mid-sized basin and large basin at the time, we're going to use the unit hydrograph. Now fast forward 1935, 1975, 1985, when the Army Corps was already there with the Hydrologic Engineering Center, and they had released the HEC1 model, which is a hydrology model, which is a predecessor of HEC-HMS, which one of you, I believe is Danny Hunt, is using for her project this semester, right, Danny?
Yes.
Okay, right. You see, so how it all fits together. So, so when this stuff came available in the late 70s and early 80s, people like myself and others were using that or were using the same ideas. So that's when I developed the concept. I didn't develop it, I just followed the practice that for the large basin, the unit hydrograph in one whack, meaning in one calculation, was not enough because there were ins and outs in there. And that is particularly demonstrated in the experience that we had in the La Leche Basin. La Leche Basin is a 900 kilometer square. So it's only a fourth of the Santa Cruz Basin. No, not a fourth, a tenth. It's very much smaller, 900 as opposed to 9,000. But the La Leche Basin has something the Santa Cruz Basin doesn't have, which is a split in the middle. And one side is humid and the other side is dry. So that means you can't apply one unit hydrograph to the entire basin because there's two hydrographs coming out and finding themselves at different time lags and so forth downstream, right? So it was more accurate. It would be a better job to separate the basins into sub-watersheds or sub-basins and do the computation individually with different curve numbers. Because if you use if you use the unit hydrograph in one whack, as they say, in one shot for the entire watershed, you would have to use one curve number also, and that will become a difficult thing to do because the curve number varies, you know, A, B, C, D, and so forth. Okay, so that suffice it to say that at that point, we said we were justified, I think, in saying for the large basin exceeding a certain amount, we call it 400 square miles or 1,000 square kilometers. You must use modeling, okay, which was in this case. So we justify the issue of modeling. Besides, it also helps that the people that were in charge, in other words, the people that were hiring us to do this, believed in what we said. Because if they don't, they're just going to go out there and do some frequency stuff. It's interesting to realize at this point, and I don't want to sidetrack on this one on different issues, but it matters a lot that the person that is hiring you knows the stuff. If they don't know, they don't do it. They won't do it. Okay. So these people really knew and they wanted to do it. They were some people, advanced people. There was a doctor out there in the Piedmont County Authority. And they said, well, we're going to go with a more elaborate, the fancier, if you want to call it that way, computation. So they hired me. Okay, so the basin, let's talk about the basin. Let's keep going in here because otherwise we're not going to finish. So I already talked about the basin. You can see in there in dark area, it goes into Mexico, 14% or 13% goes into Mexico. Now let's take a look at the river in here. The river is like this. This is the headwaters. It comes like this. You follow the arrow here, my mouse. Right? Are you following?
Yeah, we can see it.
Right? I'm following my mouse, right? This is
we can see it.
In Spanish, Rio de Santa Cruz, right? This is in Spanish because it's in Mexico. Then it goes through Nogales, and then to Nogales, there's two Nogales. Nogales, Mexico, and Nogales, Sonora, Mexico, and Nogales, Arizona. Then it goes to Santa Cruz, and the Continental gauge is one gauge, one USGS gauge, and the Congress gauge and the Cortero gauge. Those three gauges were designed. We were supposed to use those as benchmarks for the passage of the flood. The city of Tucson is right there in southern Arizona. The city of Tucson is about 40, 50 miles north of the border. Okay, most streams in the Santa Cruz Basin are ephemeral. So here we have a problem from the standpoint of modeling. Ephemeral rivers have a tendency, they're dry and they're wide, and they have a tendency to abstract the flood, meaning send it into the groundwater. It's been known very well for a number of years that if a flood runs over those rivers, it would, by the time it gets downstream, it'll be half of the flood, or perhaps even less. It depends on the flow, etc. So the flood needed, or rather the fact that there's transmission losses along the channel made it necessary to model the transmission losses. However, I should mention to you that we realized at the time that the HEC1 model was unable to do that. How fascinating. How is it that the Army Corps of Engineers HEC1 model was unable to take account of the transmission losses? And the answer is because they were going to use this model throughout the United States, but they didn't or wouldn't consider the special case of Arizona. And not only Arizona, there's California too, but Arizona more, because Arizona has more ephemeral channels. I'm saying that just to say it, but I think Arizona, it's Arizona. It's so arid zone, basically. People argue as to the origin of the word Arizona, by the way. Check it out on Google. I do believe came from arid zone, but people disagree. Some people say it came from something else. But anyway, it's arid. Arizona is arid. Although there are some parts that are not arid. I mean, if you go up North Arizona, you get into the forest, the pine forest of, what's the city there? Well, it doesn't matter. The point is that not all Arizona is arid. The event, during the last week of September 1983, and this was, by the way, associated and very much related with the El Nino event. The El Nino 1983 was the strongest. The El Nino happens off the coast of northern Peru. It's like an eye of a storm that it propagates itself throughout the year, and it affects it affects the Pacific, the Eastern Pacific, and they say that even gets to the Western Pacific. I don't have any data because I don't practice in the Western Pacific, but in 1983 we have two events. We have an event in the Colorado, and then an event in the Santa Cruz River. Two events that I know. There may be more, but I just didn't I was not aware that those things did happen. We have the Colorado event, which we have recorded now. We have a video to show that, and I think many of you have seen the video. And if you have not, I urge you to check it out on my website, the video on the failure of the Glen Canyon Spillway, 1983. That was June 1983. And then in October 1983, we also had, I have a reason to believe that they were somewhat related. I'm not a meteorologist. I'm not going to get into the details, but coincidentally, this stuff happened in October of 1983. 6 to 8 inches of rain fell over a period of 6 days, constant. It was not really a flood. It started to rain very little. People did not concern themselves. But usually it rains out there, it rains a day. In this case, it rained 6 days and it dropped 8 inches. Not only was it dropping 8 inches, but it dropped 8 inches through a very large, practically the entire southeastern, 1/4 of the state of Arizona was flooded, or rather was subjected to this very, very minute rainfall, 6 to 8 inches in 2-3 days. It extended about 6 days, but mostly it was on September 30 and October 1st and 2nd. It lasted until October 3rd. And needless to say, the volume, because of the large coverage, aerial coverage, the volume was huge, and it created this huge flood. There were 2 bridges that were destroyed. $500 million of the time was the cost of the time. Now, $500 million of that time would be at least a billion or $1.5 billion now in constant dollars. So flood damage was extensive. There was a couple of bridges there were torn apart, destroyed. There was one bridge out there in an Indian reservation that I visited, and I don't remember the exact dates. And unfortunately, I had a picture, but I missed it. I misplaced it. I'm sorry about that. I could have shown you that picture. That was an interesting picture because it showed the bridge, the concrete bridge, intact. Nothing happened to the concrete. However, on the right side, let's say the bridge was, I don't know, 300 feet? Yeah, let's say the bridge was 300 feet. Well, there was a hole about 150 feet on the right side, not 150, 100 feet. There was a hole on the right side, which basically made the bridge inoperable. Meaning what actually had happened was that there was erosion, there was a whole lot of water, the water went through the bridge, and it started encroaching upon the abutment, one of the abutments, the weaker, for whatever reason, that always happens. And it just eroded the heck out of the abutment of this right abutment of the bridge, and that was the end of the bridge. It needed to be repaired. You see how these things happen. By the way, when rivers do that, when rivers charge, they do that. They change the geomorphology. There's all kinds of things, and I could get in there, but I'm not going to, as to what actually happens when the geomorphology of the floodplain changes due to river and flood action. So kinds of stuff. So let's take a look at the project. The project, a fresh appraisal of the surface water hydrology was indicated. Evaluation seeks to determine 100-year frequency floods. So we need to reproduce this stuff. And we have some data. First, the peaks were estimated by USGS at 45,000 CFS. The continental gauge, 52,000 at Congress and 65,000 at Cortero downstream. Okay, so we looked at the modeling strategy. Okay, this is the issue here. We faced an issue here. Don't forget, this was 35 years ago. And at the time, we were kind of, I guess you could say, new to the area of modeling. I had been hired at San Diego State in the year 1980 to teach hydrology. So I started teaching hydrology. And 5 years later, I realized that I knew the subject. I thought I knew the subject. And because I've been teaching it for 5 years, and I decided to write the book on hydrology. And I did that from 86 to 89. So, and this comes even after when we did this project. This project was done in 85. So with all the experience of this project and all these other stuff, the teaching and so forth, I decided to write that book. Okay. And it was at about the time, by the way, that we developed this idea of dividing the bases into 3. We already had the division between small and medium because all of the hydrology manuals in California, they have 5 or 6 of them in Southern California, were separating the applicability of the rational method between half a square mile and 1 square mile. They said that more than 1 square mile, you can't do that. You got to apply the unit hydrogram. So that was clear. The issue of how to divide the basins between mid-size and large was a little bit fuzzy. But National Weather Service had a concept. They said that rainfall has a way of occurring as cells. 400 square miles was the biggest that they figured out. So we figured in one whack, 400 square miles was big enough to use that as a measure of the mid-sized basins. So we drew the line at 400 square miles. Everything above 400 square miles was going to require routing, require fancier computer application. Right now, we would do it with HMS, some of the work that Danny Hunt's going to do. Now, the HMS model, though, can handle anything. It can handle small, medium, large, anything. It's not limited. So it's up to you to make those decisions. Now that we have routing tied up with water quality, so much the better, because water quality usually has small basins. So at that point, when you introduce water quality and they're not just water quantity, then the applicability of the models becomes a little fuzzy. You can say the model applies to any basin. Because one thing is physics, mechanics, floods, and another thing is constituents, chemistry. That's a different ballgame altogether. Depth area relation, this was a can of worms. We could not finish the discussion of this. The can of worms, because everybody knows that when the area increases, the precipitation, the percent point precipitation decreases. But then the issue is how, and how do you apply that to various sizes, various climatic conditions, and so forth. And we couldn't get a hold of that because NWS did not help completely. They were still studying the problem. So we used what was available to us. We used the 30 minute to 24 hour depth area reduction. This basically says that for an area of 100 square miles, for a 30 minute storm, you have to reduce to 60%. For the 24-hour storm, reduce to 195%. Whatever it is, we put these curves into the model. We had a model that would pick up this, digitize these figures and put them in there. You could either put one that was a standard or one that you specifically developed it. Basically, at the time, to be honest with you, hardly anybody knew about this problem of percentage of point precipitation. And I have not pursued this subject in the last 20 years. I'm hoping that by this time we have a clearer picture of this. This is for Southeastern Arizona. We were able to pull something for Southeast Arizona from a NOAA report, recent NOAA report, recent of the time. So we use these charts in order to do the depth area reduction. Model calibration, model overview. Now we're going to do the model overview, and I'm going to describe in here our model, the model that we built in 1985. We were mimicking what HEC1 was doing, with the difference that we were introducing the Muskingum Conch in there, because we did not believe the Muskingum. We thought that the Muskingum Conch was better than the Muskingum, and the HEC1 only had Muskingum. We introduced Muskingum Conch in there. Interestingly, 5 years later, only in the year 1990, HEC1 introduced the Muskingum Conch. So now they have it. Now the Muskingum Conch since 1990 is part of HEC1. And it was, I must say that it was largely to the work that we did, because they invited me and they had a video of my presentation over there. And then they decided later on that they wanted to do the Muskingum Conch. Now, to be honest with you, I'm going to insert a little bit of the politics in here. I believe the reason why they did that is because SCS was on top of it and was getting ready to use it. So they figured there wasn't going to be, the Army Corps wasn't going to be left behind. So this is true, by the way. And then they used the Muskingum Conch, because some people out there felt that Conch was okay and Ponce was following Conch, right? On the stuff, the stuff that Conch presented cannot be argued. You may say, well, whatever it is, but you cannot argue with that. Okay, it's mathematics and good physics. So stream channel routing, we did the Muskingum Conch, we did the reservoir routing, the data requirements. We created our own topology. In 1984, I sat down to do this. I was young and eager and capable, I guess you could say. And I developed this thing, which is a plus and a minus. The plus is that it covers anything and everything with this system of numbering the watersheds, which only we use, by the way. I don't see anybody using this kind of stuff. They use different topologies, but not this topology. That's a plus. And a minus is that if you add another channel in there, you got to redo the whole thing. You could do it. I mean, you could make it automatic, but the point is that's a minor minus, I guess, minor drawback. So we have this topology, as you can see. we divided that basin into 191, I believe, sub-basins, of which we all had to have some data, by the way. So it was very intensive data collection. In places that were difficult access. To be honest with you, we had to do some guessing, and maybe 20% out there had to guess for similarity and so forth. We had to do something in terms of gathering the data, because you know the Musqueam works with slopes and cross sections. Now the slopes is easy; you can get them out of the maps, but the cross sections you got to go out there and actually visit or do something about how you set up the cross sections. But we did all of them, 190 of them. It took a while. But once you know how to do it, it's quite fast, by the way. I figure it probably may take me 2-3 months to do this kind of work. Never mind that I was teaching at the time. So 2 or 3 half months. So a month and a half, maybe up to 6. 6 months, half, so 3 months. 3 months of work. It's not a whole lot, by the way. Usually on the project that I worked on over the last few years, it's been always 6 months involvement in any. On the Pantanal, it was a year involvement. In 1995, the entire year 1995 of my life was taken on studying the Pantanal, which we cover in environmental hydrology, not in this course. So hydraulic data. In the hydraulic data, I'm going to speed up in here, otherwise we're not going to finish. In the hydraulic data, we had to estimate the infiltration rates. We gathered the data. We have some data from Matlock. This was the data from Matlock, I believe, right? Matlock was a professor out there, I think, and he gathered this data for the infiltration rate. He said as the velocity increased, the infiltration rate also increased, which I have a tendency to believe that is correct. And then finally, at the end, we justified, through the calibration, we were able to justify Matlock's calculations and Matlock's data on infiltration rates. This is the rate of infiltration in the channel bed, so that the flood, as it goes through the channel, will be abstracted. Interestingly, though, I should mention this, I must mention, that we measure the width of the Santa Cruz over at the Continental and those places out there at about 1,000 feet. It's a very wide river, 300 meters, right? But then I ran into Webb's, I believe it's Webb's. I ran into Webb's book, Professor, I believe he's a professor out there. If he's not a professor, he's a very knowledgeable guy out there, morphology in Santa Cruz in Arizona. And he gave me a copy of his book. His book is called Before and After. Like he took a picture before, like old picture, like 150 years ago, or he got a hold of that picture and then he took a new picture and he compared on the same side, both of them, and showed how it has changed. And he showed that the Santa Cruz had widened about 200%. In other words, it was 300 feet, now it's 1,000 feet. And so the before was in the year 1920, 1930, where there was no pumping. So ideally, or actually the way Well, I think is his name, or Webb, the way he explains it is that, and he's correct though, that when they started the pumping of the groundwater in Arizona in the 40s and 50s, they basically the channels widened. The channels widened. The geomorphology changed. So now we have a wide channel because the groundwater is very low, because it has been pumped. Why? Because Arizona started to develop as a state and they needed water and they don't have any water. They simply don't have any water. Now they got some water from the Colorado River. But at the point they were pumping, and as a matter of fact, we know that pumping has been done in Tucson, and also in Phoenix. Those are the two major centers out there. I don't have the data to show you, but I know positively that a lot of pumping has been done in those areas, and the groundwater has been depleted extensively. I just read, somebody sent me news, something about a news report, or actually it was an article on the water problems of California. And they're saying that up north, people are pumping the groundwater all over the place. And they mentioned a number which is hard for me to believe. They said something about 200 feet. I'm not quite sure. I have to go back to that. But there's a lot of groundwater pumping and depletion in California right now, because technically there's no regulation. I believe Cassidy is going to be talking about that. But remember, even we talked about this already. We said that in the next 30 years, we're going to establish a regulation of groundwater in California. This is a subject in environmental hydrology that we will begin to cover this week. So I'm just going to skip there. So basically, I don't have any more time. So I want you to review this paper and read it carefully. Okay, it's easy to read because it doesn't have any equations. Okay, local storm simulations. We did some simulations. Oh, important to say is that we we had a problem in the modeling, and it's a very important problem. How do you apply the rain? What rain do you apply? Okay, so we had to apply a constant rain throughout the basin. That was for the calibration. But then for the actual modeling, we had a choice. We could apply a constant rain throughout the basin, or we could apply a storm in a specific part of the basin, which is, this is a large basin. It's 3,500 square miles. It is likely that in some other storm producing or flood producing event, not the entire basin is going to be covered. So we looked at the 3 gauges and we applied floods on a real flood, upstream of it only. And we could do that because the model allowed you to apply water in any place out of 191. So we did that, we did this. It was a simulation and it worked out really well. I believe it may have been the first time that anybody did that. In other words, run a calculation where you don't rain in the entire basin. But we were justified because this is a large basin, 3,500 square miles, right? So then we revised the discharge and we came up with these values: regulatory and design discharges. The regulatory is for the floodplain and design for the bridge, actually. So the design was 80,000 at Cortero. Never mind that the Cortero maximum measured by USGS in 80 years, and the 80 years of record was 27,000. 27 times 3 is 81. So we ended up with a value of 3 times as much. We compared it with regional data or basic formulas, and it quite didn't match in here. You can compare in here how the risk value is too low. The others are a little bit higher. Okay. One could argue that why did you do so much work? Because Bouton and Renard did something similar. Not quite. You can see there's some differences in there. We believe, of course, that you can do global lump computation and you get a number, but you cannot explain all the details, where we were able to explain all the details. So I stop in there and saying that comprehensive computer modeling capable of simulating handling of the complex topology of the entire basin, driven by 100-year frequency floods. How many watersheds? Typically, we believe in this kind of calculation, one should do between 50 and 100 watersheds. More than 100 is too much. In this case, we did 190. We were trying to show the model. In the next project, I think we're going to do about 50. So I will stop there. And again, I urge you to read this paper in detail. And now I'm going to move on. We don't have more time here. Onto this other project. In the year 2008, I did this project in Peru. There was a friend, an acquaintance or friend of mine who runs a company in LA. And one day I met him accidentally and he said, "What do you do?" I said, "I do hydrology." And I happened to have my book handy at the time. This was like 20 years ago. So I handed him my book. He was an important guy. See, here's my book. And he looked at the book, and the next day, because we were staying at some hotel out there, the next day he says, "Ponce, I do structures. But we kind of structure civil. We have projects that have bridges and so forth. If I do a hydrology project, if I ever get into hydrology, I'll call you." Sure enough, 5 years later, he called me up and says, "Here, it's me. I've got a hydrology project for you." It was this project over here, the Leche River flood control. The objective was to determine or design the hydrologic design of the dam. So we were working on a team of 7 people, and I was supposed to supply the dam designer with hydrographs, the design hydrographs. And there's 2 or 3 design hydrographs. So we were to calculate the design hydrographs. So we went out there and we look at the project description. And we decided as a group that we were not going to do one dam on the river because it was like, that was the old concept. It hadn't been done here at the Domenigoni Dam up in Hemet. When they did that, I was aware of that. When they did the Domenigoni Dam up in Hemet, they had 4 sites, and 3 of them were on the rivers, and one of them was offsite, and they decided to the offsite, even though it was more expensive. Why? Because the offsite was not going to collect sediment as much as the inside in the river, on the river, the dam on the river. So with that experience and other experience that were being discussed at the time, I recommended that they do 2 dams, one on the river and another one on the side, particularly since a dam that had been built by the Germans, so a German company in the 70s, south of that region, the so-called Tina Jones Dam, which I visited and I have a bunch of pictures of it, had performed really well, because at the time we did the last measurement, the last measurement of sediment was done, or sediment accretion, it was 8%. That was 10 years ago, 8%. But compared to the dams that were put together by some other European companies that I don't want to mention at this point, the one in the north, in Piura, was 58%, and the age was the same. So one filled 80%, no, 8%, and the other one 58%. That is a clear message that the dams on the river doesn't work, at least from Western Peru, which has a lot of sediment. In no time, you get to like 4,500, 5,000 meters, that is 15,000 feet of altitude. Very, very short, in short distance. And therefore, it was necessary that we do this. So it was accepted, and this stuff is there. And we have the 2 dams, La Calzada, flood control very good, water storage fair, service life short, meaning it's going to fill with sediment. Calicantro, the opposite. So we went with both of them. So that's as far as the design is concerned. The basin description, the basin looks like this. It's extremely hilly. I believe the average is 35%. This is the I guess you could say the western, the Andes are divided into western and eastern, or occidental and oriental. And this is the western slope of the western Andes off the coast. So rock outcrops and agriculture, the tremendous amount of agriculture on the slopes. I had never seen what you see in there, agriculture on the slopes. The fact that they could do it. In many books, it says that the steeper the slope, the less you should do agriculture. But no, these people are doing agriculture, and apparently with not a whole lot of negative effects like gullies and things like that. Typically, when you have agriculture on a slope, eventually within a few years, you develop the gullies. But in this case, no gullies. And there's photos that I have, other photos, because I was there for a year, off and on, 3, 4, 5 times. So we had a lot of chance to take photos of everything that was going on in there. Okay, so we have the climatological stations. This is a gauging station. The model description. Okay, and we call our model rainflow. By the way, we haven't used this model in about 10 years now, but primarily because we cannot compete with the Army Corps of Engineers, because the Army Corps of Engineers has the seal of institutional conformity or something like that. I don't know how to describe it. People prefer to use the Army Corps because they're protected against liability and so forth. So basically our model is a good model. I guess it must have served as a prompt for the Army to put the Muskingum Conch into their model, because we were the first ones that did it. And once we did it, they said, oh, well, you know, but I do believe at this point, and I'm going to say this because it needs to be said, that it was the move, the positive move of SCS at the time, the Soil Conservation Service, that convinced the Army that they had to do it. And they must have had some people are smart that read the Conch paper and realized the Conch was all right and it was correct. And all we did was just implement the Conch ideas. So the Muskingum Conch was incorporated into the model. Okay. The model is, the morphology out there is extremely, with a lot of hills and so forth. We have this, it's called Lajas de Tongon Mountain, near the confluence of the Moyan and Sangana. The Moyan and Sangana get together at some place out there and form the La Leche. La Leche. La Leche is the Spanish for the milk, by the way. The Moyan and Sangana tributaries next to this place meet to form the large river. It's a large river. Data needs are the following: basin topology, geometric properties, hold on a minute, terrain slopes, storm precipitation, hydrologic soil groups, Manning's in and cross-sectional geometry. We had to run through the entire basin. Those places where we could not access, we had to kind of simulate and do some figuring out what we were going to do. Basin topologies. You can see the basin topology is not that augmented or very large like the other case in the Santa Cruz. We have about 26 sub-basins in here. The way this is done is like this. If you care to listen, you identify third order, second order, and then first order. And then you number first order with a 1, the second order with a 2, 2, 2, 2, 2, and then third order. And that's it. Once you give numbers to these reaches, that's it. You say, well, this reach, this is the data, and that's it. You still have to have an algorithm for it to pick it up, though. That's not easy to do, but it can be done. So this is the basin. This is the basin, and we did by hand at that time. It was funny. At the time, we could do it by GIS, but we decided to do it by hand because we love doing it by hand. We're old fashioned, right? Doing watershed delineation by hand was fun for us hydrologists, right? And if you did it by machine, you took away the fun, naturally. So we did it by hand. And I should tell you at this point that I had done a calculation for a basin over in Tierra del Sol, where I worked for 10 years. And I gave it to a student. I said, you apply GIS to this and see how much you get. And she got about 85%. In other words, ours was 100 and hers was 85. But that's, of course, an error that cannot be sustained. It's too much. Like I could take 1 or 2%. So the machine is not perfect. The GIS is not perfect. Our calculation following the peaks and saddles was perfect. And this is a calculation that follows the peaks and saddles, meaning by hand. You may not be convinced by it because I believe at this point, nobody's going to pay it. They're just going to go and say, well, do it the way it's done. Never mind, there's errors. They really don't care. They can't prove it. You cannot prove it unless you did a heck of a lot of work, and nobody's going to do it because we have gone beyond that. But at this time, we were, I mean, still in the area where we could do it by hand. So I'm justifying myself in here. Then we calculate the principal spillway hydrograph, the emergency spillway hydrograph, and the freeboard hydrograph. There's 3. The principal spillway hydrograph is the 100. The emergency spillway is 100 plus 26%. These are criteria that have been developed by the Soil Conservation Service, now called Natural Resources Conservation Service, in their manuals of practice. Okay, so that's the emergency spillway is the P100 and in excess of 26% of the difference of P100 and the P10,000, and so on and so forth. The pre-work hydrograph is the P10,000. That's the worst. We are designing for 10,000. Okay, we don't design for any more than 10,000 because 10,000 is considered to be 400 generations of human life, and that's a lot. But nature has a lot more than 10,000, 50,000, 100,000. There is a mention in the report from Katrina report by a gentleman that must have, a gentleman or lady that must have not been a hydrologist or rather a geotech, because that was a geotech problem. The failure of the Katrina dam was a geotech problem. So they must have, that committee must have been populated by geotechs, and they made a mistake. They said that the calculation of the 100,000, I mean, nobody, I don't think anybody does calculations for 100,000. We did it for 10,000. And I urge you to examine this scale, the definition sketch, because it's important for us to realize that we have the retarding pool storage before it gets to the overflow. This is free overflow in here. Then the surcharge storage in the overflow, and then we have the freeboard. All dams should have a freeboard. So the first thing, this is A to fill, B to fill, and C to fill. In the extreme, you will fill C. What happened in Oroville was that it was over here. Are you following the mouse? The level was over here. Then within a few days, it rained a whole lot and it went over here. It went over here in the regular spillway, the auxiliary spillway, which was around here below, and it broke it. It destroyed it. We have pictures of that, and you've seen it. This was February 10, 2017, when the first spillway, it was called the regular spillway or something like that. It broke, it destroyed. So then the state of California, the Department of Water Resources, decided to go for the big one, and they said, well, what the heck, we lost one spillway, but we're not going to lose the second one. So they let it fill up and start overflowing, and sure enough, within a day or a couple of days, the other one, once it had a sufficient head, it also was failing. That's when I told the students, I remember I told you this, or I may have told some of the classes, let's pray, because if it continues to rain, it's gonna go over here, it's gonna fill out this blue, light blue area, and it's gonna go over the dam crest, and God help us. The dam's gonna breach. It was an earthen dam. It was a high 720 feet earthen dam, the largest height or the highest of its time when it was built in the early 60s when Reagan, I believe, Reagan was the governor of the state of California at the end of his, well, whatever, 1960s, okay? I believe it was Reagan. So fortunately, it stopped raining. God listened to us. It stopped the rain, which, by the way, may have been actually generated by El Nino, because 2017 was an El Nino year. Peru suffered a lot. Every time there's an El Nino, Peru suffers. Peru is the first one that suffers because it's the eye of the storm or the phenomenon. There were a lot of bridges that were destroyed in Peru. Oh, I mean, I cannot believe to tell you the disaster in 2017. It was in March, I believe, February or March. It was at about the same time, by the way. Okay, so it's all related. You can see the geography, this whole thing along the Pacific. El Nino is like that. El Nino, as you know very well, we know that recurs every 14, 15 years. We have 83, we have 98, we have 205, and we have 217. But of course, this 14, 15 years is not constant. It varies. It varies, and it could do whatever it damn well pleases. Excuse me. Whatever it wants to do, it will do. We cannot control that. We cannot say this is going to be an El Nino year because we're waiting for it. No, it may happen, it may not happen. That's the characteristic of meteorology, by the way. So hydrologic soil groups, we picked up the curve number, Manning's cross sections, storm frequency modeling. We have a lot of tables in here. I urge you to review this report in its detail because it is very instructive as to how these things are done. Because sooner or later we're going to run HMS, and you're gonna be faced with the same situations. So it's good for you to learn from our experience so that you would know what to do in case you were to do this kind of calculation later on. So we got the model results, all the tables. We have a bunch of tables. Oh, by the way, I decided to put the tables over here. I was not going to load the report with tables, so the tables are all outside of the report. As you can see, this is a tremendous amount of work. Okay, it took us a year to do this work, by the way, a complete year. Typical reach cross-sectional data. Table 11, design storm precipitations, everything. You can imagine, you got a rainfall, you got to figure it out in space and time. Spatial distribution, temporal distribution. Then when it hits the ground, you figure out the topology. Then once you do that, you have to figure out the unit hydrograph. And this operates with the unit hydrograph, by the way. We use the Soil Conservation Service unit hydrograph. Now, people may say, this is Peru. This is not, the Soil Conservation Service applies to the US. Okay, well, there's a caveat for that. The Soil Conservation Service divided the US hydrology from the standpoint of storms in 4 parts, A, B, no, 1, 1A, 2, and 3. And those of you that know your hydrology must be familiar with this. So then we chose the one that was similar. Out of the 3, I'm sorry, out of the 4, the one that was similar to the location in Peru, because we do not have a Peruvian distribution. We simply do not have. People are there and not, they haven't gotten into that. The soil conservation got into that in the 80s or 70s, early, because they needed to do it. They had the wherewithal, they had the personnel, and so forth. They have the resources, and they did it. They did a good job. Those 4 type storm from the Soil Conservation Service. Okay, but so we had to do it. This reminds me of a story. I went over to, I was supposed to do the same thing, but in Mexico, in Tijuana, and actually it was in the Alamar. It was in the Alamar-Tijuana River Basin. Now, you should know that the Tijuana River is about 3,500 square miles, out of which 2/3 are in Mexico. Because the line that splits California and Baja California, Mexico, is a line, it's a straight line. And it hits 1/3 of the basin on this side and 2/3 on the other side. So when we did the modeling of the Tijuana Basin back maybe many years ago, like 20 years ago, we had to look at the Tijuana data. The data for Tijuana, rainfall for Tijuana. So I went over to the think tank, the Mexico Water think tank, which is out there in a place they call, I forget. It's an institution, the water. It's an area of the water agency, okay? And so I went in there, and I know some people over there. So I went over there, I visited them, because it was important enough for me to visit. You know, you have a visiting presence is always better than on the phone or whatever. Although now we have changed that with Zoom, but that's not the story 20 years ago, right? So I went over there and I talked to this gentleman who was in the know. And I said, you know, I want temporal distribution, Mexico, applied to Mexico. And I was hoping that he was going to say, well, we got 3 or 4 areas, you know, the wet, the dry, the very dry. Mexico has very dry. The driest in Mexico is Baja California Sur, the Vizcaíno Desert. That's even drier than Baja California, okay? And the wettest is in Chiapas, in the south, next to Guatemala. Chiapas is a rainforest. This is small, but it's a rainforest nevertheless. Well, the other one is a very super arid desert, okay? So they have all kinds of and you know very well that desert is not the rainforest, because the desert never rains, but when it rains, it blows everything apart. And in the rainforest, it rains all the time, but it rains softly, smoothly, right? That's the characteristic. So there's totally different hydrology. So I went over there and asked for the rain distributions. And the gentleman, I'm telling you the truth, he pulled out of his office, and he showed me a piece of paper. He said, well, this is the stuff we use. It was not a report, it was just a memo from memo of practice that they did. And he showed one distribution to be used in Mexico. So I could not help but ask him. I said, do you use this both in the north, which is dry, and like Chihuahua is dry, and in Baja California is somewhat dry and then very dry, or all the way to Oaxaca, Chiapas, it's different. He said, well, you know, Professor Ponce, I'm sorry, but that's all we use here. So I basically decided that I was not going to be able to get any help from that standpoint from Mexican hydrologists. So then I decided to do the sensible thing to do, which consider, and allow me to say this, it was that Tijuana, I was so close to to the US that it could be considered part of San Diego, right? So we apply the rainfall that is San Diego rainfall to Tijuana, because we didn't have anything for Tijuana that would be justified for use that originated in Mexico. So with that, then I have almost finished in here. I'm I went too fast actually, that's okay. Let me get in here. Conclusions. The deterministic conceptual distributed rainfall runoff model. Is deterministic? Yes, it has the Muskingum conch. It's not Muskingum. Is it conceptual? Yes, it used the unit hydrograph. The unit hydrograph is not deterministic, it's conceptual. It's a concept that was developed by Sherman based on the substitution, lagging and adding and so forth. You learned that from your studies of hydrology. Is it distributed? Yes, it is. It has 27 basins. Each one could rain differently, could move differently, and so forth. That we call distributed. Interestingly, this basin over here had two areas over here. Let's go back in here. It had two areas. The area over here was dry. This area was dry. And this area over here was wet. And this in the middle was kind of transitional, because it's always like that. So we had to apply different rainfalls and so forth. We made it distributed. And as a result of that, interestingly, as a result of that, where am I here? We came up with this. Look at this. These are the principal spillway hydrograph and the emergent spillway hydrograph. There's a principal spillway with 4,000, the emergency, no, 3,500, 4,000, the peak, and this one is 6,000. So this is the worst. This is for the freeboard. So the first one's going to fill this part over here, right? The second one is going to fill this part, and the third one's going to fill that part, right? And we have, but look at the shape of the hydrograph. It's an odd hydrograph, right? Most hydrographs are sinusoidal, but those are theoretical hydrographs. This is a real hydrograph. This came out from the modeling. We obviously have two peaks in there, only that the second peak is obliterated a little bit. It's kind of obliterated. Since the storm is the same, basically, it is the same. It shows up as the same. And why do they have this thing in here? Because that's just the way the system works. There are, in the middle of it, there's generation of a lot of water, contribution from some basins, and that's just the way it comes out from the model. We can tweak it. I mean, we can change the model. We can change slopes. We can change anything. But why? I mean, the slopes reflect what the slope of the terrain is. One thing that is really important in here to figure out is that if we did not a type 1, which we used, but a type 1A SES, we would get a different hydrograph, obviously. But we chose out of the 4, type 1, type 1A, 2, and 3, to choose the type 1 because that was the one that most amenable to the conditions, to the kind of arid, semi-arid conditions in the half of the basin. So we did that, and we figured out the flood discharges. So basically, then we're going back in here. It's used to calculate design flood discharges for proposed in-stream in La Leche River. Calculations for a proposed off-stream dam at a neighboring site at Cali Country are also performed. The model is driven by suitable frequency-based 24-hour storm. These meteorological events, which recur every 12 to 15 years, produce unusually large amount of precipitation. Everybody in Peru, from a hydrologic standpoint, if not from every point, is concerned about the damages that El Nino could cause. And really, there's not much we could do about it. Really not much. We have to be prepared, do the best we can, redesign the bridges. I developed an idea which is called the forebridge, which is don't do bridges outright, because the bridge, you have to do it extremely huge to cover everything, and people claim that there's no money out there. So do a forebridge, do a system that will behave as a bridge whenever it has to behave as a bridge, and then it could behave as a ford too. And I thought that I had developed the concept of the forebridge usually, but I was wrong, because 2 years ago, right before the pandemic, I went to Sinaloa, Mexico. on some personal story. I had to do something personal out there, right? Not gonna get into details. And I ran into the Sinaloa River, and the first thing I find is this ford bridge on the Sinaloa River, which might have been there for at least 5 or 10 years. So I figured those people beat me to the game. They actually had built, not just talk about it. They actually built a ford bridge. Okay, and there's other four bridges out there that I've seen, mostly in Mexico. There's one out here. If you care to look at it, you can go out there to the Pala Casino, and before 5 minutes before getting to the Pala Casino, if you take off from I-15, you run into a fort out there. I'm hoping that it's still there. The last time I saw it was 5 or 6 years ago. There's really no reason why they should replace that. Obviously, the bridge is better than the fort, but the problem is that the bridge may fail, as we have seen many times. Sometimes even the fort failed. There was a fort and I think I've shown you that I already exceeded my time. There was a fort on the Mojave River, run by Ellendale, up in the center of mid-center California, north of well, you know, out there. If you don't know Ellendale, look it up on the map. Ellendale, Helendale. Mojave River, which is an ephemeral river, runs over there. And the Mojave River hardly has any water. So they put a fort together because it has no water, they put a fort. Back in the year 2005, they had a huge flood. Interesting, the 2005 was also El Nino year, mild El Nino year, but El Nino year, nevertheless. They had a 2005 flood, and in the year 2005, they had a flood, and it all but erased the fort. It erased the fort. Professor Ponce is Mr. Lucky, Dr. Lucky, and I was there a couple months later. I was at a party out there, and I ran into this lady. And we got to talking, and she said, well, what do you do? I said, well, I teach hydrology at San Diego State. And she said, really, hydrology? You want to see the pictures I took when the fort failed? I said, oh my gosh, sure, show them to me. So she gave me a CD with about 20 or 30 pictures, which I subsequently posted on the web. I can show you where they are, of the event. As she didn't take a video at the time. It was not popular, but she took a whole bunch of pictures of the failure of the fort out there on the Mojave next to Ellendale. So with that, I am going to stop, and I have a meeting at 7 o'clock today. So let me just say, see you on next Monday. We're going to continue with the project. So I finished with this project. I'm asking you to read it in detail because it may be on the exam.